just yeah.
Why have I got this microphone?
To project.
Oh, I don't really need it.
So then they can hear us, I think.
Oh, yeah, they should, yeah. Short time?
I think we do. Yeah, when you start talking, I'll just check they can hear us. Okay. But it's fine. It seems okay.
All right. This is not working. No?
I think
working.
Yeah, it's working.
Okay. Hi everyone. I was going to say good morning, but it's good afternoon. Hello. You get me today, not Tammy. Sorry. Tammy's had enough of linked lists, so I get to continue today on linked lists. My name is Sasha. I lecture this course in term 1, sometimes in term 3, but not this year because I get the joy of doing a different course, which, dare I say, is a lot more fun. But only because it's game design, not because 1511 is not a fun course, because obviously you've all handed in your assignment 1 and you all had an absolute ball doing it, no doubt. Okay, so linked lists. How is everyone feeling about linked lists so far? Loving them? Yeah, bit of thumbs up. Usually this is really, Gab, I've never done a lecture with you moderating before. Can you do a poll? How do we feel about linked lists? Please, thank you. So I can see how you're all feeling about linked lists. So what we'll do today is we'll go over what Tammy kind of did. And then we're going to learn how to insert anywhere in a linked list and also delete from a linked list. All right, let's get started. So I think last week with Tammy, you guys worked on creating a linked list, so building up that very first node. And then Tammy finished with inserting a node at the very end of a linked list. So we're going to go through that again and also talk about some of the cases that you can have, the special cases. You also traversed a linked list, and I think you printed out the linked list. And so let's today build on that. And today we're going to insert anywhere in the linked list, and we're also going to delete from a linked list. And we're going to talk about all the special cases that you get when you do anything with a linked list. So all the things that you should be thinking about. So for those of you that are feeling a little bit, this is all getting too much, know that linked lists are actually a really complex data structure, not usually done in introductory computing, but we like to push the boundaries and we think that you are capable of learning about linked lists. So just know that it is kind of like a hard thing to learn, even if the concept seems to make sense. Putting it into practice is a whole different thing. And then for some of you, for some reason, linked lists will come a lot easier than arrays even. So, but for some of you, not so much. So, be nice to yourself. The code is I think Gab will post that into the chat where the code is. Okay, so let's just quickly run through a rehash. What are linked lists for? Any takers? What do you think linked lists are for? I mean, it's there, but anyone, what would you use it for? This beautiful data structure. What's it good for? Why do we need it? Why do we want it? Why do we care about it? Yeah.
Dynamic, adding values to dynamically.
Yeah. So that is the key reason we want a linked list, because in an array, once I create an array, I'm kind of stuck with the size of that array, and it's really hard to insert something into the middle of an array because I'll have to move everything after it by 1. Whereas with a linked list, it's all about dynamic memory allocation, which means that I create whatever I want. I create a node whenever I need it, and then I insert it wherever on earth I want to insert it, and I don't have to worry about running out of space, and I don't have to worry about moving anything along. I just insert wherever I want. So you've heard me use the word node. That's what we call an element of a linked list. and many nodes make up a linked list. Well, actually, even one node can make a linked list, or you can have a linked list with nothing in it, which is just nothing in particular. Okay, I should probably look at how that, how was the linked lists? Everyone is doing quite good with linked lists. Okay, so I'm just going to rehash for everyone else, and then we're going to run over the code line by line as well, which is something that I love to do. So each node basically, and this is why, for those of you that were wondering, why are we learning about pointers? What on earth is the reason for it? Well, one of the reasons for it is that you then get to learn how to use a linked list, because linked lists, because we're dynamically allocating memory, we want to know where that memory is located that we've allocated, so we can, so we don't have to be in that contiguous array kind of structure. So in a node, what we might have one piece of data or many pieces of data, but what makes it a node is that there is a pointer to the address of the next node. It's like a little bit of a scavenger hunt. I don't know where the 5th node might be or the last node might be. I always have to start at the beginning and follow the trail, because each node only leads me to the next one. There are different types of linked lists where that structure is not quite the same. I might have, links that go both ways or links that go in a circular order. But in this course, we're only learning a single linked list, which means that the scavenger hunt only goes in one direction. So you really have to go visit a node to go to the next one, to go to the next one, to go to the next one until you reach the end. And how do you know that you've gotten to the end of a linked list? Null, that's right. So the last node is going to be pointing to a null pointer, and that means you are now at the end of a linked list.
Can you move the camera to the other side, at the bottom of the slide?
Which camera?
The one that streams. It's covering a bit of the text on the slide.
Oh, I understand what you're saying. That took me a while. It's been a while since I've done one of those. How's that? My slides are made for a left side. Okay, great. All right, so, and then a linked list is basically made up of many nodes. Okay, so fantastic, I've got many nodes, and I join them together. Each one leads me to the next one. How do I know where I've started my linked list? How do I know where to go to the beginning? What do we call that? Yeah, we call it the head of the list. So the head of the list is not a node on its own. The head of the list is usually where I just store the address where that first node sits. Okay, so the node is still a separate thing. But that head over here is just a pointer to where that first node sits in memory. And then that will have the next one and the next one. And then what happens is then I finish it up with a null to say I have reached the end of the list. Okay, so a list with 1, 3, 5. So the head pointer, keep in mind it has its own memory address. It's not the same as the memory address that it points to, as is the beauty of pointers. And pointers, they make always so much sense when you're kind of learning about them in theory. And then when you put them into practice, that's when it goes kaboom. And that's where lots of mistakes happen. And that's why C is such a really lovely language, because you kind of get to have all these kabooms, which means that you learn a lot about how computer memory works as well, which is really nice when you're just starting to get your head around all the basic programming to then suddenly have to deal with memory as well. But I promise it is worth it. Okay, so how do we create a linked list? I think maybe let's go to the code and go through the code that Tammy did, and then we can just run through it line by line, and that will be kind of the rehash of that, and then we'll do inserting into a linked list and do, yes, that is what I wanted to do. Okay, so I'm going to go through this piece of code from the very beginning to kind of give you an idea of what's going on. Okay, so the first thing that we're doing in this piece of code is that we are creating a node. So I am defining a struct node, And the reason it's a struct node, because I'm creating a structure to house different types of things together, and it's going to have some sort of int data. If you've noticed in the lectures, we often use int for data. It doesn't have to be an int, but an int is the easiest thing to demonstrate with. It's like a basic component, but it could be a char, it could be an array in there, it could be really anything that your heart desires. And then what's going to make it a linked list is this lovely thing here, which is a pointer to the next node. So it's going to point to the address of the next node. Okay, so that's fantastic. I've done that, so now I'm kind of ready to start building my linked list. So I go over here and I start to build my linked list. So first of all, in this line of code, I basically make a pointer to called a head. So this is going to be a pointer and it's called head. Excellent. I haven't assigned any values to it yet, but then I move to the next line and I'm assigning to the value of head. I'm calling the function create node and I'm giving it 5 and null. Okay, so I've called this function. Hello, create node function, where are you? I'll go down to where that function is, and now I get to actually do something with this function. So I gave it the number 5 and I gave it the value null. So those are the things that I've given it. So now what happens is on line 41, I create a pointer to something called a new node. So I've got another pointer now, and that pointer is going to be called new node. And inside it, what I do is I take the function malloc, which is a standard C function, and what it means is memory allocate. So I'm creating a piece of memory that I'm going to hoard for myself. And I'm saying, can you please give me size of struct node, which means that that new node now has enough memory space in it to house int data and also my pointer to the next node. So I've created enough memory to kind of house both of those components. So now I've created this lovely new node. I've given it some memory. And what the function malloc returns is it returns the address of wherever it created this. So that means inside this new node pointer, I now have the address, and I'm making this up. Let's say the address is that, and that means that that address has now gone inside here, and that's now assigned. Now, it still has nothing in it. It's just really an empty node. All I know is the address of that empty node. So on line 42, I'll say, okay, new node, in the data component of it, so in the structure, I have a data component. In that component, I'm going to put whatever was given to me, which was the number 5. That means on line 42, I'm now assigning the value 5 to it. Okay, great. Then I'm going to move into the next line, and I'm going to say, okay, I'm going to now assign the other element of that structure in it, the other member of that struct, and I'm going to assign it whatever was given over here with next, which was null, which means I'm now assigning null to it. Excellent. Now it's time for me to finish my interaction with it.
Can you turn the lights off and point at the projector screens?
Maybe. Maybe not. They are all off. I'm just going to reduce, we're just going to have a bit of ambient lighting in this whole theatre now. No one go to sleep. How's that? I hate these rooms. More, less. That's more. Yeah. Things are working really well. All the board lights are off, and basically just wants me to switch off all the lights. All the lights off. You know what? I think that they're just these ones here. No, they're not. Oh, they are. Okay. Thank you. I'll switch the back ones on. How's that? Now we can kind of maybe ensure that no one falls asleep. Okay, I hope that now that's really bright now, that red. Very angry, aggressive red. Okay, so now I've finished in this function and I'm going to return something. because I called the function, I feel like it should return something, and what it's returning is it's returning new node, which means it's returning this address over here. Fantastic. I'm going to head back up to where it has called that, now with unfortunate markings all over this screen. And what that means is that inside here where I've called it from, which was over here, this over here has returned to me this address, and that means the head is now this address. So the head is now getting the same address over here. Okay, so now this is not a new node, now this is actually the head. My head is pointing to this, so the head is going to have the address of that thing in it. Excellent. Now I move on to the next one, and I call that create node again, and now I'm going to make the number 7. Do you want me to run through the number 7 being created, or you all good? Here, there, everywhere?
Run through it.
Run through it. Okay, let's run through one more, and then we might see if then it gets too repetitive. Okay, so my head is now 0xAAA, and on line 24 I'm making another call. I'm calling that function create node, and this time I'm giving it 7 and head. Great. So now I'm going to go down, back to create node, and the values that I've given it now are going to be 7, and I've given it the head. So the head value, which is 0xAAA. Fantastic. So I go to line 41 now, and I'm going to create another new node pointer. So there's going to be one more of these new nodes. And inside it, I've got space for a data, and I've got space for a next. And I'm going to malloc some, enough size for it. So again, I'm going to malloc a node with enough space for a data and a next. And I'm going to assign some values to it now. So I'm going to go into the new node, into the data element, and assign data to it. So that number 7 is now going to go in here. And then I'm going to go into the new node, into the next component, and assign the next component in it. The next was the head, which is the address 0xAAA. Great. And then I'm going to return the address of that new node. So I'm returning, let's say this address is 0xBBB. That's my new node address, and that's the address that I'm now going to return back to my function. So I'll travel back to where the call was made from, and what I'll do now is the call was made from here. So what has been returned into the head is 0xBBB. So that's now going to change over to 0xBBB. That is now the head, but my head, whilst it's this one, is pointing to the next one is to that one. So really I should have drawn them the opposite way, but to make it, there you go, it's now going like that, and this is now the head. The head has moved to here. Okay, so I'm inserting at the head each time. Okay, run through one more, or how are we feeling? Everyone's, yeah?
So in this case, does that mean that the third node its next would be 0xCCC, for instance?
So the next one is going to be, I'm going to create, let's say, 0xCCC, and that's now going to be the head, and it's going to be pointing to whatever the head used to be. So it's now going to point to this one, because that's what the head used to be. So every time it's going to insert at the start, point to the one that used to be the head, and then so on and so forth. So what you end up with is something that looks like this in this particular list. So in this particular list, you're going to start out, and you're going to, I'm going to start out from the back, because otherwise I'm going to run out of space. So first up, you're going to create a node with 5 and null in it, and that's your first node, okay, and that's the head. Okay, then you're going to create a node with 7 and point it to the node that used to be the head. So you're going to have 7, it's going to point to this one because that's what used to be the head, and it's going to become the new head. Then you're going to create the next one, which is 11. So you're going to create the node 11, and you're going to point it to the head. So that means you're going to point it to this one, and it's now going to be the head itself. Okay, then you're going to do the next one. This is the longest list ever. I don't know why I created such a long list. And you're going to create one that's got 18. It's going to point to the head, which was this one, and then you're going to change the head to be over here. And then finally, you're going to do one more. It's going to be 1 you're going to point it to the one that used to be the head, and the head is now going to go to this one. So you're going to get this big list that kind of looks like that. So at this point in time, what you're printing is 1, 18, 11, 7, and 5. And that's your list starting from the head going down to the tail. Okay, then Tammy then went on to insert at the tail, I believe. While she went through the traversal of a linked list, maybe we'll traverse the linked list next. So how do you call this print list function and print it? Let's quickly look at that. Hope you're enjoying my crazy lady drawings. Okay, print list. Here we go. And we're over here. So when we print the list, what I'm sending to this function is the head, which means I'm sending the address of this node over here. So let's say this is A, B, C, D, and E, let's say as the addresses, and then this one goes to nothing. So I've given it the address of A because this function, the input is a pointer to the head, and it's returning nothing. So it's a void return because we're printing out. We don't need to return anything. We're not changing anything. We're not manipulating anything. So what I'm doing first is, and this is kind of good practice to do this when you're kind of playing with linked lists, is I'm saying I'm going to have a current pointer and I'm going to assign the address of head to it. Why do you think it's good practice to kind of do that? And in this particular case, it wouldn't even matter so much, but why do you reckon it's good practice normally? Yeah.
So you don't accidentally modify the original head?
Yeah, exactly. So once I start moving through this list, I won't know where the head of my list is. So I will not be able to go back to the head of the list. I'll just lose that pointer because remember, it's a scavenger hunt. You only know who's following you. You don't know who came previously to you. So I want to always know that in the head is the head of the list, and that's that. I'm not modifying that. So what I'm doing is I'm creating a pointer current. I'm setting it to the head of the list, so the address that the head of the list is at. And that means I can now modify to my heart's content, and the head of the list is safe, the address of it. So then I go through into my while loop and I say while current is not equals to null. Okay, current is currently at the head, which is this node here. Is current, so is the address of this node null? No, it's not, which means I'm going to go inside the while loop and I'm going to print out whatever is inside the data component. Inside the data component is 1, so I've printed out 1. Now what I do next is I start traversing the list, which means I need a way to move on to the next node. Otherwise I'm stuck on one node. And the magic is that the next node is sitting inside this address here. So what I'm saying, okay, my current was over here, but now I'm saying I am assigning to current. Remember, we do the right side first. So I'm going to say current next. So I'm accessing this element here, and the next is pointing to B. So current next is B, and I'm going to assign it into current. So that means my current has now moved over here, and it's now got the value B in it. Great. I'm going to go back to my loop and check again. Is current equal to null? No, it's not. There is a value to it, so it's fine. I'm going to go back inside the while loop. I'm going to print out the next thing that's inside the data component, so 18 in this case. And I'm going to shift along. So I'm going to first access whatever's sitting inside next, which is C, and then I'm going to assign that value to the current. So that means my current will move over next door. Okay, great. Back into the while loop. Is current equal to null? No, it's not. It's now equal to C, so I'm still good. Going to go inside this while loop and I'm going to print out whatever the data element is, in this case 11. And then I'm going to say, okay, what's in current next? In current next is D. And I'm going to assign that value to current. So my current is going to become where D is. Back to check the while loop condition. Still good. I'm still D, so I still have an address in there. I'm going to print out the number 7. And then I'm going to shift along. Current next. In next is the E's. And I'm going to check. And then I'm going to assign current to it. Fantastic. Back to check the condition. Is current equals to null? No, it's not. It's still E. So I'm going to go in there and print out again. I'm going to access whatever is sitting in the data component. It's 5. And then I'm going to take whatever's sitting in current next, which is null, and I'm going to assign it to current. So then current is sitting over here now. And what I'm going to do, back to the while loop, is current equals to null? Yes, in this case it is, which means I'm now out of the while loop, so I've broken my loop, and now I come out here. Now it's a void function, I don't have to do anything, and that means I'm done and I can return back to the main from the call. Yeah.
The only reason for the first line is to preserve the value of head, right?
Yeah.
So that we can keep track of where it is, so we don't modify it.
Yeah, so it's standard, it's kind of good practice to do it. And in this case, it wouldn't have made a difference because I'm just traversing the list and not doing anything to it. But it's good practice to just always kind of have this, almost always you'll have this struct current is equal to head, just so that your head is preserved at all times so that you don't lose track of where the head is. Yeah.
Aren't these nodes coming from the struct new node? Like in line 51, you're taking it from node, but aren't the nodes up top that you put in red from the new node you created?
So every time I created the new node, I assigned it over to heads. So then it would lose, like when I was returning a new node, all I'm returning is the address of that node, and that address was being put into the linked list. So when I created the linked list, they're no longer called new node because I was assigning them to the head and inserting them at the head each time. And new node is just a variable name basically.
And the head belongs to the node?
And the head is the top node that will then have each next in that head, going to the next one, going to the next one, going. And if you remember, my 5 had a null in it, so that means it was the last element in my node, and all of these I actually assigned a value to them to take me to the next one. Yeah, so new node is just a variable name like A, B, C. It's just a way to keep track of that address of the node that I just created so that I don't lose that. And then I insert it into my linked list, and then I don't care about new node anymore. I'll just keep reassigning on top of it. Yeah.
For this course, is it recommended to add nodes backward or forward? Like they're adding here backwards, right?
You will get asked to add nodes at the front, at the back, in the middle, anywhere, based on some condition. And in the real world, obviously your problem will, depending on your problem specification, you will decide which way is the best way to add these nodes based on what problem you're solving. Yeah.
If they ask,
Oh, sorry.
if they ask us just create a thing, what should we, whatever.
You know what, mostly you will get told, or the context will tell you how to add them, but it will be specified for you where to add the nodes when you're creating your list. We'll never leave you kind of guessing where it should go. Yeah.
With line 51, struct node head,
Yeah.
can we think of it kind of like an array? Like you just give it the address and we know the whole.
So, it's similar in that sense, is that struct node head has the address of the first node, which means you know the rest of it because you can follow the path, but it's different to an array because arrays, it's all contiguous, so you just go one over. Whereas in memory, a linked list is like if you've got, I've drawn all over it, but I'm just going to go again. Let's say you've got, and this is a very basic interpretation of what it looks like, but this is the reason really for these linked lists is that let's say this is my memory, right? When I create these nodes, it doesn't look for a block of memory. What it looks for is just small chunks that are available. So I might get, my first node is over here, then my next node might be over here, my third node over here, and the only thing that keeps me going from one node to the next is the address of the next node, and that's why I can't lose sight of the head because it's got the next. So this is what tells me where to go and in which way. So every time you've seen these linked lists, they're drawn beautiful, linear. That is not what they look like in memory. In memory, they're all over the shop, and it's a scavenger hunt. You've got to go to one place to know where to go to the next place, to the next place, to the next place. That's the only way you can do it. Yeah.
Can you reiterate the question?
Can I? I sure can. And the question was, I've forgotten what the question was. The question was, is it the same struct node head? Is it the same as kind of giving it an array because, once you know that top element, you know them all? And I was saying it's not quite the same. Similar in the aspect is if you know the head of the list, you will be able to follow the kind of the hunt to get to the rest of the nodes, but it's not the same in that, you know, an array, once you know the first element, you really know them all because they're contiguous in memory. They're just one after another. So you can access, you know, you can access any of the elements in an array. Whereas in a linked list, I won't be able to go to my fourth here without going, you know, first to the second, to the third, before I get to the fourth. Yeah.
Before you had struct node pointer equals to malix.
Yeah.
Now you have struct node current equals to head. What makes this different to the one before?
Okay, that's a really great question. The question is, before I had a struct node, new node, and I had malloc and I made some space, whereas in this case I have a struct node current is equal to head, and what makes them different? So the difference is, in this current case, I am not creating a new node. Okay, all I'm doing is I'm saying I'd like to place the address of a node that already exists into this variable called current. That's a pointer, so it's keeping a memory address. Whereas before, when I'm creating a node, I'm actually making a whole new node. And when I make a whole new node, I need a place for that little node to go. So that's what the malloc is for. The malloc is creating a little space in memory for it. And I only do that if I need a new node, because otherwise it's a waste of memory to just create new nodes for no particular reason. Yeah?
Can you make a linked list that makes a node in the main function but points to a different function? It makes a node in a different function.
Yeah, okay. So a linked list, so, okay. Oh God, these are very good questions. Hey? I've got to repeat the, and it's also 12:40 and I haven't done any code yet. The question was, can I make a node in a different function, return to main, go all over the shop, and so on and so forth? That was the question, right? The question, so because I'm creating memory, what I'm doing right now is I'm going to need to kill that memory at some stage, which is what we're going to do. Otherwise you're going to, well, it's not likely to happen in modern day computing, but with really large programs, you will run out of memory if you don't end up freeing that memory. Although when I reach the end of the main, it will all die, really. But if I get stuck, or if I have a while loop that doesn't end, and I keep creating memory, I will be in trouble. But yes, the memory persists until I kill it, okay? It's like I'm hoarding chunks of memory, basically.
Use that memory in a function.
Yeah, so if I'm creating that node in a function, I'm passing that address to my main, I still have that memory, that's not gone. And that's part of the reason why I can make this dynamic memory allocation to the node. Okay, great. I feel like, we haven't done insert at the end. This is, how am I going for time? This is a classic Sasha situation. Time means nothing to me. Okay, I'm going to, you know what, let's just do it anyway, and then it's Jake's problem on Friday, so hope he enjoyed his trip. I'm going to erase some of this, and then we're going to okay, so we've got this lovely list, and now what we want to do is what's the next thing? We've gone back to the main, so we finished this print list, and now we've got a function insert a tail, and we're giving it a 12 and a head. Excellent. So let's go down to the function which is insert at tail, and that's inserting at the end of the list. So I'm going to just nope, that's not what I wanted to do. I'm going to erase this, and let's go to this function, and we'll talk through this function, and then we can do some new code. Okay, I pass to this function, and since I'm not using my terminal actually for now, for a second, I'm going to just do that. Okay, so I've passed to the function 12, and I passed it the head of the list, okay? So that means right now I've got my data is equal to 12 has been assigned to it, and in my head is the head of the list. So whatever the address of this is, it's A. That's what I've given this function. Okay, great. So now over here on line 65, I'm making another pointer, and this is a pointer, and so is this, and that pointer is called current, and I'm assigning the value of head to it, which means I'm giving it this value A. Excellent. What am I going to do now? I'm going to traverse this list, so I'm going to move through it. So I really want to, you know what, I'm going to kill off a few of the, let's pretend that this list finishes here, because otherwise we'll be here forever. So this list now has 3 elements in it, and let's say this goes to null. Okay, and none of this is happening. All I know is that this is the head, and this is now also the current. Okay, fantastic. So whilst current next is not equal to null, so you might notice that this is now different to when we did the print function and we went till current is not equal to null. Why do you think in this case it's current next is not equal to null? Yeah, so it just makes a difference whether you go to the very last node and stand on the very last node, or you go past the last node. And each one will be different depending on the context of the problem you're trying to solve, okay? So I'm going to check if whatever's inside next is not equal to null. So in next is the value of this node. It's not equal to null. Great. I'm going to go inside this loop and I'm going to start traversing. So current is equal to current next. So that means my current is now going to take the value of the next one and it's going to move over here. Excellent. Back to my while loop condition. Is current next? Is whatever sitting inside next equal to null? No, it's not. There's still another node pointing to it. Enter into the loop and say, okay, now I'm going to assign the next value to it, which is C, which means that my current is going to go next door again. I'm going to go back and see, is current next is not equal to null? Well, current next in this case is equal to null, which means we come out of that loop. And what that means is at the end of this loop is I am standing over here. And the reason for that is I want to insert at the tail of the list. If I would have said current is not equal to null and I would have gone past and stood over here, I wouldn't have been able to insert because I wouldn't have known where my previous node that I need to connect to. So I would have gone past the level where I can insert. Yeah?
Yeah, if each next points to the next, how come it doesn't just point all the way to null and loop straight away?
Well, if you pointed this one to null, what would happen is you would have no idea where those 2 other pointers are because they're just anywhere, right? They're not contiguous, and that's why.
Like if A next is pointing to B next and B next is pointing to C next and C next points to null, wouldn't it just follow all those components the first time and go straight to null?
Say it again, sorry?
It's hard to explain, but like if A next is pointing to B next and
Yeah.
B next is pointing to C next and C next is pointing to null, wouldn't it, when it was checked, the pointer follow all the way to null?
So A next is pointing to B. B next is pointing to C. C next is pointing to null in this case. Okay. All right, so now we've come out and we're sitting over here right at the end of the list. We're perfectly primed for insertion. And what we're doing next is we're saying current next. So whatever is sitting in here, I'm going to call the function create node. I'm going to give it the data. Data was 12, and I'm going to give it a null. So I'm going to go back to that function create node, which is up the top here. And I'm going to create this node. I don't know what's happened to the drawing. There we go, we're back. Okay, so I'm going to create a new node, that means. I've given it 12 and I gave it null, so in this case it's going to be null. So here I'm malloking some memory for it, which means I'm going to create a new node pointer, and I'm actually going to create the pointer and the memory for it. It's going to float somewhere in my memory, but it's empty right now. So now I'm going to assign it some values. So the address of the new node comes from this piece of, comes from the malloc function where I've created some memory, but I need to keep track of where I've created it. So let's say this memory is a D. It's never going to be this pretty, but there we go. That's the address of it. But now I have 2 parts to it. So in data, I'm going to assign data to it, which is 12. And the next, I've given it a null to assign to it. So now I've got this beautiful node. It's located at D, and I'm going to return the address of it. So which means I'm going to return that D back to the function that called it. And the function that called it was right here at the end, which means what I'm saying here now is current next is equal to whatever is sitting inside this create node. So create node returned D, and that means I now want current next to point to D. So instead of this null that it's no longer pointing to, I now have my next node that has 12 and null in it. So what it means is I've created a node and added it at the end of the list, and what I've done then is returned the head of the list. Why do you think I've returned the head of the list there? Because who cares? I've inserted at the tail. It's not like my head has changed. Why do you reckon I returned the head?
Sorry guys, can you guys all be quiet? Otherwise the people online won't be able to hear.
Yeah,
what I should say.
bit of shush. Why do you reckon I've returned the head? I've inserted at the tail. Anyone? Anyone? Yeah.
The next time we traverse the list, we want to start from the first element.
Pardon?
The next time we start traversing, we want to start from the first element again.
I mean, that is true, but the head is still the head. Why do you think, what, I mean, that's, yes, but what is another reason why I returned that head? Yeah.
We want to replace its value with the new one.
No?
You can access everything from the head. It's like returning the whole list.
Pardon?
Isn't it because you can access the whole list from the head? So it's
I can access the whole list from the head, but I've inserted at the tail. Why do I want it, the head hasn't changed?
because you want the entire list. When you
I
say
do
return
want the
head,
entire list, but I already have the entire list. I know where the head is, I haven't changed it.
let's return.
The head can change.
How could the head change it?
It goes there.
Yes, thank you very much. If it was empty. And that is one of the beautiful cases that is going to stick in your head. What happens if I have an empty linked list and I am now inserting at the end of it, which is really also at the front of it, and that means my head is now changing? Yeah.
Will the code break if it's empty though? Because you're accessing for it next, and it's going to be null.
Exactly. So in this function right now, it would break because on line 68, so line 65 would be fine, it would just assign null to current. But on line 68, when I say current next, what I'm doing is I'm trying to dereference a null pointer. I'm trying to go inside that null pointer and somehow get a next address, but there is nothing there. I haven't assigned any values to it. So in this case, this function would actually break, okay? And if I had an empty list, it would not work. So what you want to be doing is you always want to be considering what happens when the list is empty. Yeah.
That just doesn't make sense to me because if like the cut out, if the size of your list is 0, like it's empty,
Yeah.
then that while loop shouldn't work. But then like who cares about what you return? Like as in if your head's your tail and your tail's your head, like it doesn't really.
So if the list is empty and I have the line of code that actually checks for that, okay, then I'm going to do something different because it's an edge case. But I'm returning the head, and usually it's kind of, so because if my list had nothing in it, okay, and I've inserted that one node into it, that is now the head but also the tail. And that's why I return the head to it. I know. It's such a vibe when you first hear about linked lists. You really, the one thing about linked lists, and I don't have a lot of screen space, so my drawing is really messy. But the best thing you can do with linked lists is draw it, okay? Because then you can physically see how many nodes you have and where the mistake will happen and where you might need to insert and what might happen. So I'm gonna erase what's on there now and draw it for you.
Before you erase it, can I ask you another question?
Yeah.
When you assign 12 to your tail,
Yeah.
shouldn't it have been 11? Because that was your seed. Like if you bring back the red drawing,
I
like
could have.
12 was the head, the original head. That was the data in the original head.
Okay, I could have actually. Oh, okay. So when I called the function, I've given it two values, 12 and head. So when I came here, this data is equal to 12, and this over here is equal to the address of the head.
Yeah, but so when you're while loop, you're asking for like your current to the next,
Yeah.
which is not equal to null. So that's your second last i.e. the one before your null, right?
Yeah.
And you want the data in that.
No, I want the data, I want a new node to follow that node.
Right, but where do you want the data to come from, your original head?
No, the data is coming, I'm giving it over here at insert. When I'm calling the function, I'm saying I can have 2 nodes with the same value. I can have 3 nodes with the same value. I can have as many nodes with the same values as I want. But over here, when I call the function inserted tail, I'm saying, can you do it? And I want the node to be 12, and I want it to have the address of the head because I'm going to walk through the list to the end of the list. And then the data that I want inserted at the tail, I want it to have 12 in it.
Right, okay.
Kind of.
Like 30%, 35%.
This is an excellent percentage to start with linked lists. I tell you what, linked lists are hard. And once you throw memory in, that's when things become really hard. Yeah?
Could you please explain why the list is empty?
Why the list is empty? Let's say I have nothing in this list, okay? I am giving it like this. Okay, I'm going to erase this in the most... Okay, so let's say I'm going to call my insert. So I've got the struct node head, fantastic. And then I'm going to say, you know what? I'm going to call insert at, oh gosh, this name, 12. I guess you've all seen my desktop. You probably all have thoughts about how I name my variables. Those thoughts are probably correct. Insert add tail. Let's say I'm going to call it here, okay? I have nothing yet. Okay, so the list is nothing. All I have is this struct node appointed to a head, and it's got nothing in it, but I'm going to say head is equal to that because otherwise I'm going to lose, well in this case, otherwise I'm going to lose the node, but I wouldn't normally have it because I'd normally have a list. So let's say nothing, don't do that. Let's just say keep it simple. I'll call inserted tail here, and I'm going to give it a different value. Okay, let's give it the value 1 just to, okay. I'm going to get rid of this. Okay, so I've called this function inserted tail, and let's say I go over here, and I've given it the values 1 and head. Okay, right now, it's going to fail so spectacularly because the head has absolutely nothing in it. It's nothing. There's nothing going on. So I'm going to pass it some data, and as soon as I'll go to here, this is going to say, okay, current is equal to null. Maybe I should write stuff down. Where did I drop the pen? Okay, so I've given it a 1, and let's say I've given it nothing, null, there is no list. And that means here, it's going to be okay. It's going to say current pointer. Okay, that's still okay. I'm going to give it null. And then I'm going to go in here, and I'm going to say current next. And nothing's going to happen because I'm null. I'm now going to go into null, trying to get more null. It's going to break so spectacularly. It's just going to kaboom. So what we always have to do in code is kind of safeguard for this situation. And you'll see this a lot in the first few kind of cases when you do your code will be these edge cases that might happen in a problem, and an empty list is often one of those edge cases. How do you think I can check for whether or not I've got an empty list? What do you reckon?
Check if the head is null.
Yeah, I'm going to check if the head is null. So if my head is equal to null, then what am I going to do? What do you reckon?
Just create the node.
Pardon?
Just create the node.
Yeah, I mean, I can exactly just create the node because I'm inserting right at the tail. So I'm going to basically do this, create node. Now, that's great. I'm going to create that node, and then I'm going to exit out of that if statement, and I'm going to potentially run into the same problem again. How can I kind of safeguard that if statement as well? Is it complete right now? I've created a node. I don't really know where that node's been created. I've lost that piece of memory because I've returned something from the function create node, but I haven't stored it anywhere, so I don't even know where that node is now. Does that make sense, what I've just said? Or not particularly yet? So right, what do you think I should assign the return of that create node to something? Yeah, I'm going to pop it into my head. And then what do you think I'll do after that? I'm going to return the head because there's nothing else that I need to do here. And things are working out well. And that means I've now taken care of an empty list and I'm not going to break. Any questions? No questions? Oh, one question.
So how would you access, so say you have a linked list that has like 10 nodes, right?
Yeah.
How would you get to a specific node that you want to get to? If you don't know the address of the pointers that point to each node.
What a fantastic question. You're basically asking for those online. How do I get to a node? Let's say I want to get to a 5th node out of a 10 node list. And if I was moving to schedule, you would have already learned how to do that. But I'm not moving to schedule, so in fact you're going to learn how to do that in about 10 minutes. And now potentially is a good time for a 5-minute break before we return, and then we're going to move through the list and then we're going to delete some things. Okay, 5 minutes, because I feel like this dark atmosphere also is just inducing sleep. Okay. It's going well. I'm already behind schedule. I haven't even done any new content yet.
It's so dark in here. Oh, it's gone out.
It's gone
We're
out,
in the
though.
middle. I'm going.
Okay, good for you.
Yeah.
Done with work. Nothing's working.
I'm done with life, and yet here we are.
Good gap.
They're over there. Okay.
Alright.
Kahoot or not Kahoot?
What happened?
Line by line.
It's also my problem. Keep me in. Do you want to mark all the players? Do you want to mark all the games?
Okay. All right, I was told it's an abomination if we don't do a Kahoot, so we're going to do a Kahoot. Is that right, Tammy? Where's the music? Isn't that why everyone likes Kahoot? And then we're going to compile our code, which is always very exciting. We'll see what breaks, and then we'll do a few other functions. Oh, someone's got a sad face on a linked list. Oh, I do love the names. Name. Jake's toenails, disgusting. That's a good one. Are you saying the person next to you though? All right, let's do it so that we can keep going. That was a hard question. I didn't even mention it today. Okay, I'll mention it after this. Well, the person with the frowny face seems to be doing well right now. How lovely. Okay, so the function is called size off, and we give it what we want the size of, otherwise it doesn't know. Ooh. Okay, so what does the stab do? That arrow, it basically does whatever the star does with the value in brackets, and it's so that it doesn't get super confusing having lots of brackets in one line. It's the shorthand way of doing it. Okay, we'll talk about that. I think that says to stop, not to top. So what happens if you want to stop on the last node of a linked list? Okay, we'll do that in a second. I'm just going to... Apologies for all those that were... Okay, if you want to stop on the last node of the linked list and not go past it, just like in the print list function, we go past it because we want to travel to every single node. But if you want to stop on the last node, you want to check that the next value in that last node is null, because that means you're standing on the last node. And we will talk more about it when we delete, if hopefully we have time to delete. Okay, and last question. The question is wrong, so it's a trick question. You just have to guess. That's even better, because I was like, that's a long piece of code. Just guess. Let's see how good you are at guessing. There you go. It's gone a lot faster. Excellent, a few people did. Good luck with that. Woo! Yay! Who's Nick? Who's Nick? He's Nick in a off. Gab is busy up. Ask Gab to throw the lollies, but currently busy. Who wants to throw some? Thank you. Over there. Oh, oh, never again. Never again. All right, good job, especially on that last question. Okay, and back to VS Code. I think it's high time we compiled something. Let's compile. Ah, compiles beautifully. Okay, that is awful. Okay, my goodness, I should have really checked what the list was. Okay, so the first list should be, oh, of course, it inserted at the tail number 1 and there was nothing there, so that's this one. Then it inserted 18, 11, oh, this is a mess. What a mess. Let me just get rid of this for a second. And save this. And let's run it again. Okay, so now it's gone 18, 11, 7, 5. 18, 11, 7, 5. And that's this print list here. Then it inserted 12 at the tail of the list. and it did something, and then we're going to print the list again. So it's gone 18, 11, 7, 5, and then the 12 that it inserted at the tail, and that's this print list. So that's at least doing the right thing. Okay, we're happy about that. Okay, now what happened here? If we inserted at the tail, it was an empty list. Okay, so I'm going to save it. Now I'm going to run it again, compile, and we've got a bit of a situation here. And that's because up here I've got a struct node head. There's nothing going on. It's uninitialized. So let's say I initialize it to null to start with. Okay, and save that again, and let's run it again. Compile and run. And what's it doing now? It's now doing something here. So it's done something here, maybe, I don't know. But then it's got 18, 11, 7, 5, and then it's got 18, 11, 7, 5, and 12 again. So why does it look like over here it did nothing? I don't see that one. Where did that one go? What happened to the one? Why did that one come out? It...
the second line after, the first line after you replace head with the null.
Okay, so over here I've got head is equal to null, which means I inserted one null, so I potentially created a node with one null.
But then after that, where you have head equal to create 5 nulls.
Yep, yeah, that's right. Yep, perfect. On line 25, I killed that node that I created by basically saying I'm going to insert a 5 null, and that means I've now lost that node that happened over here. It doesn't destroy it. I still have the node. I just don't know where on earth it has gone. Okay, so we're going to otherwise the people online cannot hear anything, even though I've got a very loud voice. Okay, so I think we should write a little function to traverse a list again, and then we're going to maybe use that function to insert anywhere in the list, perhaps insert at a particular position, because I just clearly come up with examples on the spot. Okay, so I think it's useful to know the size of the list. What do you think? Should we find out the size of the list? So let's do a function that will find out the size of the list for us. What do you think that function would return? What do we think it will return? Int. I agree. It will return int. Going to be really creative. I'm going to call it size of linked list. And what do you think I need to give this function? Head. Absolutely. Whenever I want to do anything with a list, I literally just want to give it the head of the list, because it allows me to know really the whole of the linked list. If I know where the head is, I can follow it along. Okay, great. I now have a stub for this function. So let's, every time. Okay, so now let's go and actually write this function. Let's go to the end, and let's go here. Okay, so I've got a function, and that function is going to return Okay, great. Okay, what do you think I need to do to find the size of the list if I was solving it just logically? Let's say I've got some sort of linked list. What do I need to do to get the size of it?
Start at the size of 0, and then loop through the entire list adding 1.
Yeah, I just need to count up each node. I don't need to do anything to it. I just need to traverse that list and count it. Okay, fantastic. So the first thing I'm going to do is I'm going to, what do you think I will do first? Okay, I'm going to give it a struct node current, and I'm going to make it equal to head, even though I'm not manipulating anything, but just in case. Okay, what else do I need to do? I return some sort of int that gives me the size, so I probably need a variable to keep track of whatever this size is. So I'm going to have a variable int size. Probably a good idea to initialize it as well. I'm going to make it equal to 0, and then we'll talk about what that means. Okay, what else? Should I start traversing? It's probably everything that I need. Yep. Okay, so to traverse the list, okay, I'm going to have some sort of condition in the while loop. What do you think that condition should be? Should I go through every point in the list? Or should I stop at the last point in the list? Or should I go past the end of the list? We can try both and see what it gives us. So what do you think? What do you want to try first? Current is not equal to null? Oh, wrong place. Okay, current is not equal to null. This means that we're going past the end of the list, and we're going to, when we exit this while loop, what that means is that current is going to be equal to null when we're exiting this loop. Okay, that's what it means. Okay, so great. Whilst current is not equals to null, what do I want to do? Yeah, I want to increase the size by 1, and then what do I want to do? Yeah, I want to move on to the next node, okay? So that means I'm going to traverse. You're going to really, after the second assignment, you're going to be dreaming of this current is equal to current next. That's going to be your whole life for the next 2 weeks. Enjoy. Great, fantastic. And then what should I return over here? Size, yep. Okay, let's see what it gives us. Okay, we've got this function here, and let's go over here and we can print the list, and over here we will also print out the size of the list is something, and we want to call our function, I've forgotten what I've called the function. Yes, that's correct. And I'm going to give it the head. Okay, so let's see what that gives us. Okay, compiles, always a good first step. Okay, so first 18, 11, 7, 5, the size of the list is 4. Do we all agree with that? Yep, we do. And then I've got, the second part of it over here. So fantastic, we've traversed the list. We now have, that the size of the list is equal to that. Okay, what do you think would have happened if I was instead going for this situation? Current next is not equals to null. Okay, what do you think would happen then? Would I be short? Would I be long? What will happen? What number do you think it will output for me? Yeah. Yes, I am now, yes.
And on the right side.
What's it showing right now?
You might need to make it point back at you and
Hi.
retrack it.
This is really just weird, just forcing it to look at me. Okay, it's kind of seeing a part of me, so that'll do. No. I'm so short and still it doesn't want to. Okay, that should do it. Yep. You don't need to see the top of my head. My hair's all slicked back. Okay, what do we think it's going to return here? 3, okay. Let's run it. And it does return 3. Why does it return 3? Because it's stopped when current next, well, there's 2 reasons why it returns 3. One, because we've stopped at the last node. However, we should have still, so, okay, let's draw it, and then you will see why it returns 3. Okay, So let's say I've got this list, and this list inside it has so right now we've got 18, 11, 7, and 5. Okay, this is my head. So when I go inside this size, I say, okay, current is equal to head, which means my current goes over here as well. And I now have a variable called size. It's equal to 0. I go into my while loop and I check, is current next? So is this node here not equals to null? No, it's not. So I'm going to go into the while loop. I'm going to increase the size by 1. And then I'm going to move along the current. So the current is now going to go here. I'll check again, is my current next? So is this node here not equal to null? That's good, it's not equal to null. I'm going to increase the size by 1, and I'm going to move my current along by 1 as well. So my current is now going to sit here. I'll go back again and I'll say, okay, is my current next equal to null? No, it's not, so I'm good. I'm going to go back here, increase this by 1, and I'm going to move my current along by 1. Okay? And then here I'm going to say, is current next not, well, current next is now equal to null, which means I'll break out of this loop. And that means what's happened is I haven't counted the last node because I never went into the while loop to count it. So in this case, I mean, you could modify it by changing where your counter starts counting, but you could just do this, and then that means that you've visited every node and you've gone past the end of it, which means you've counted every node. So be careful of that error, that does come up. Okay, should we try inserting in the middle? How does that feel? Insert in the middle or insert it at a location? What do you want to do?
At a location.
At a location? Okay, let's insert at the location. So let's say over here, I would like to insert at the location. So I have many options for me. I could insert over here, I could insert over here, I could insert over here, I could insert at the end. We've dealt with that case. I could insert at the head. We've dealt with that case. So now we want to be able to kind of insert anywhere I want to insert. Okay, let's insert at position, I don't know, after the second node. Okay, and then we'll talk about all the things that could go wrong and all the things that could go right and all the magic that can happen when you insert. Okay, here we go. Let's have a function. It's going to be insert at location, and I should give it the node that I want to insert, so I should give it some value, I don't know, 13, and then I should give it the location where I want to insert at. Oh, this is going to get wild because I'm going to give it 3 things. Okay, let's say I'm going to, after the second node, and then what else do I need to give it? What do you think I should give it? How will it know anything without... I need to give it the list itself, right? So I'm going to give it the head of the list as well. Okay, now, if we were to do it as a function, what am I going to be returning? What would this function return that is inserting anywhere in the list? It might return nothing, but it might return something. What if it's an empty list? What if it's, what if it's a list of 1 item? What if it's a list and then I'm meant to be inserting at number 1? So I'm going to return a struct node pointer because I'm going to return the head of the list just in case. Okay, the function is called insert at middle. And what I'm giving it is an int data, I'm giving it an int location, and I'm also giving it a struct node head. So I've given it 3 parameters, and they are, I'm giving it the data that I want to insert, the location at which I want to insert it at, and also the head of the list that I want to insert into. Okay, fantastic. Let's try and write this function now. Oh my goodness. I really should have just copied and pasted it. Yep, regretting this now. Okay, excellent. I want to be able to move through the list to find the location at which I'm inserting, okay? Anytime I would like to traverse my list, and that's what I really want to be doing right now, is I'm going to start by saying struct node current is equal to head. So that what it means is I've made the current node equals to the head node, and now I can use the current node to just float through my list. Okay, let's do just a very simple case. We know that we've got 4 things. We're not going to care about the edge cases right now, and then we'll try and break it. So I would like to keep track of the location and to see if I'm at the right node at which I want to insert. So that means I need some sort of variable to keep track of my location. So I'm going to have a counter. And then I'm going to start traversing the list. And let's say I want to insert it before this location or after this location. This makes a big difference too. Let's go after, just for the fun of it. And then we can talk about what happens with before. Okay, great. Let's start traversing the list. How do we traverse the list? Yeah, I think I heard someone say while. We do want a while, okay? And in this case, do we want to go all the way to the end of the list, or do we want to stop on the last element? Yeah, why do we want to stop on the last element? Yeah, in case I have to insert after it, so I want to know where I am located. If I want to stop at the last element, I'm going to have current next is not equal to null. Okay, and then when I move through the list, I always current next. Okay, now what am I doing as I'm moving through the list? What should I be checking for before I move to the next node? I should check if I'm at the point where I want to insert. Yeah? Yep. Yep. We feel good about that? How will we check that? And how are we keeping track of which location we're at?
If counter is equal to location.
Yep, okay, sounds good. If counter is equal to location, then we're going to begin the process. Oh my God, my spelling today is really going well. Then we're going to insert. Okay, great. At some point we want to be changing our counter as well. We want to be counting, and perhaps we want to be doing that here so that we can actually keep maneuvering through. But if counter is equal to location, that means I would now like to start the whole insertion process. Yep, I want to insert that node in the place. Let's do it in a diagram, and then we'll do it in code, okay? Because it makes it a lot easier once you see what is going on. Okay, so I think I gave it, I can't remember which values I gave it. Anyone? Does anyone know? No one remembers. Okay, yeah, good. Everyone's doing well. And it's only Monday. Okay, 13.2 head. Okay, so far in my piece of code, I've given it 13, location 2, and I've given it the head of the list. So what I have right now is I have my data is equal to 13, my location is equal to 2, and current is equal to head right now. Okay, and I want to insert it after this node over here, okay? So if I'm moving through it, okay, let's see what happens if I'm moving through it. I'm just trying to remove all the extra stuff so it's not as confusing. Okay, so this is my list right now, and I want to insert it at this point over here. Oh, which is actually the middle, how convenient. Okay, I'm moving through this list. So my counter is also equal to 0. I'm going to go into this while loop and check is current next is not equal to null. No, it's not. And now I'm going to check is counter is equal to location. Counter is equal to 0, location is equal to 2. So it's not, which means I'd skip this if statement, whatever it had in it. I'd increase the counter by 1, and I'll also move the current to the next one. So the current was here at the head, and the current is now over here. I'd go back and say, is current next equal to null? No, it's not. I'll check if my counter is equal to location. Is 1 equals to 2? No, it's not. So I'd actually skip that if statement and increase it again. So I'd go, that's 2, and my current would move along. And as you can see, I've actually skipped the point of where I could do a comfortable insertion. And what is the reason why I skipped it? Because my location is kind of saying, okay, that's node 1 over here, that's node 2, but my counter is saying that's node 0, so I'm not kind of consistently counting. Those are easy mistakes to fix. I mean, all you have to do is just start your counter at 1 and that will fix it. But now what I want to be doing is I want to stop when current is over here, okay? Because what I'll do is I'll then make a node with my 13. So that means I'm going to go create this node here that's going to have 13. And what I want to do is I want to connect my current to this node, the current next to be that one. And whatever used to be inside this current next, that's what I want to go in here now, in that next, so that it connects it like that. So I create the connections in that way. So if we're to do it in code, and then we're going to run through it again. Okay, if we're to do it in code, okay, we say we're going to start counting at 1. And over here, if they're equal, what I want to be doing is I want to create a node. Okay, so I'm going to struct node, and I'm going to call it a new node. And what I'm going to do is I'm going to create that node, and I'm going to give it the data and null. So I'm going to call the function that's creating the node for me, and it's going to create this for me, and it's going to do it with the number 13, and it's going to do it with null, okay? And I'm going to store the address of this node that I've created inside the pointer new node. So it's going to hold the address for me, which is very nice of it. And then I want to start connecting. I've got the node now, it's there. I now want to connect it in. So where my current was, okay, basically, and just bear with me, we might have to change a few things. I want the current to be pointing, so the current next, to now move to point to the new node. And I will run into the problem because now I want my new node to point to whatever was inside current next. So now I've got some funky things happening because my current next already has a different value in it. What should I do here?
You need to create a copy of current next first.
Yeah, look, what I really should be doing is I can say that my new node next is going to be equal to current node next. That's not what it's called. And then my current next is going to be equal to the new node. And that should hopefully create the right connections for me. Should we try it out? Might help to return head. Return head. Okay, let's try it out and then we can fix it once we see what's wrong or not wrong with it. Okay, let's run it. Amazing things happening. Okay. Oh, because I called it insert at middle here. What did I call it here? Insert at, okay, great. Okay, let's save that and let's run it again. Okay, what's happened? Undefined reference, okay. Okay, great. Consistency is always key. And spelling is also always key. Not a strong point of mine. Okay, third time lucky. Third time lucky. Let's clean it up. And let's run it again. Okay, so let's see what it's done. It's printed out the list for us to start with. because we've got a lot of things going on. So 181175, great. We've said the link size of it is 4. And now we wanted to insert the 13 right there in the middle, and it's done it. So it's inserted at 13, then it also inserted the 12 at the tail here, and it's done an amazing job, if I do say so myself. Who wants to run through it line by line? Yeah, line by line? All right, is that, or a question? Line by line. All right, let's line by line it. Okay, so let's say, I guess you're doing deleting with Jake. Okay, so over here we've got a list, and that list right now has 4 nodes in it, okay? And I've got, we've got 18, and let's say 18's at A, and it's pointing to B. And then the next node is going to be B, and it's got the number 11 in it, it's pointing to C. And C has the number 7 in it, and it's pointing to D. And the number, and what's sitting at D has 5 and null. And that's going to null. And this is D. Okay, and this is my head of the list over here. Okay, fantastic. So I've printed it out, I've done the size of it. Now I'm doing insert at location 13 to head. So let's go down to the function, insert at location. Okay, I am now at the function. My data is 13, so over here I've got data, I'm passing it the number 13. I've given it a location as well, after which to insert, which is number 2, and I've given it the head. And the head is currently pointing at the address A. So I've given it all those lovely things, and now I want it to do something for me. Okay, line 111, I create a current pointer, and that pointer is storing the address of head. So what's inside head is A, that means current is now storing A. I now create another variable, and that variable is called counter. And counter now also has the value of 1. Is my face in the way of the screen? Because I'm writing right on the edge. Okay, all right, okay, great. Okay, fantastic. Then we go inside our while loop and we check the condition. The condition is current next, so is whatever sitting inside here not equal to null? Well, no, it's equal to B, so that means I enter the while loop. I go in here and I check, is counter equal to location? Well, counter is 1, location is 2, which means it's not. So I skip all of this and I move down to here. Okay, I increase my counter by 1, so counter becomes 2. And then I move my current along to the next one. So current was over here at A, and now it's pointing to the next, which is B. So now current is sitting over here. Excellent. Go back to the initial condition and I check, is current next not equal to null? Well, it's equal to C over here, so it's not equal to null, which means I enter this loop. And I'm going to check again. If counter is equal to location, my counter is 2 and my location is 2. Excellent. That means I go into this if statement and I go in here. It says struct node, new node, create node. So whatever I create over here in this function and return, I'm going to store the address of that inside this pointer new node. Okay, and right now there's nothing in it because I do the right side first, which means that I'm calling the function create node and I'm giving it data, which is 13 and null. So I'm going to head to my create node, which is over here, and I'm going to go through the create node. Okay, so I've called this function and I'm going to start here. So now it's saying, okay, struct node, new node, malloc some memory for it, which means that what I've done is I've created this, I've malloc some memory, it's called new node. So this thing right now is called new node. I've given it the size of a node, which means it's got space for data and it's got space for the next. And it's got its own address as well. And that's what's going to sit inside. So let's say it's at address E. And that's what's going to be stored inside this new node. Okay, so that means that this new node inside this function currently has the variable, I should really stop calling things the same thing. It's got the variable E in it. Okay, so this one here has the variable E. Now what I'm going to do is I'm going to assign it the data, which was 13, and I'm going to assign it the next, which was null. So I've got this node, and now I'm going to return new node. So I'm going to return this address over here back to the function that called me. Okay, so I'm going to go back to the function that called, where the call came from, and I'm going to return in here E. Okay, and that means here we assign E to it. Okay, fantastic. Now I'm going to go here and I'm going to say, okay, new node next, which means whatever is sitting inside here is going to get whatever is sitting inside current next. In current next is C, which means that instead of null, it's now going to be equal to C. Okay? And then what that means now is I've created kind of this. This node is now pointing over here to whatever's sitting at address C. And then I go to line 122 and I say, okay, whatever is in current next right now, which is this thing here, I want it to point to the address of the new node. And the address of the new node is E, which means that's now going to point to E. Okay? Great, okay, so now I've killed this and it's pointing to this node. So now I've kind of inserted this node in, okay? And I'll exit out of this if statement. I'll still actually increase my counter and I'll also move my current along in this case. And then I will go back, check if current is equal to null, no it's not, and then I'll keep going through this loop because it's not an efficient loop right now. I'll just keep going even though I've done what I want to do. How can I make it more efficient? Yeah, after I've inserted it, I'm going to return after it, okay, so that I don't keep going through it when I've already done what I want to do. So I'm going to return the head at this point in time, which means that I don't go inside this loop. You know, I'll just come out of this function and go back to where it was called from. And then that's that. So now I've inserted at a particular position. Okay, what are some things that could go wrong here? Okay, what if I do have an empty list? If I have an empty list, then what's going to happen here is this is going to cause an absolute disaster. Well, I mean, in the scheme of things, not really a disaster, but in your code scheme of things, it's not really going to work very well because you're now going to dereference a null pointer, try to access something that doesn't exist. So you want to be checking if that list is empty, okay? So let's put a thing in place and check if the list is empty, okay? So the first thing we do is check if head is equal to null. And what happens if head is equal to null? I just want to create the node, insert the node. I don't know what the specification is of this problem, right? To keep it simple, I'm just going to return the head and say nothing can happen here because there are no locations in an empty list. So all it's going to do is just send back that null. Nothing's going to happen, nothing's going to be inserted, but it's not going to break at that point in time. Okay, any questions? Yeah.
Someone on the forum asked, what if location is 4? So if you want to put it at the end.
Okay, beautiful question. What happens if I want to put it at the end? So if my location is 4 and I want to insert after it. So do we think it's going to work for us at location 4? I think the best way to do it is first to run the code and then we're going to talk why it works or why it doesn't. So right now I've inserted it at location. You know what? I'm just going to comment out these things so it's not confusing. And here, let's insert 13 at location 4. Let's see if it works. Who thinks it's going to work okay? 2 people. Who thinks it's not going to work? 3 people, I think. Who doesn't care? Who just wants this lecture to be over? Just one person over there. Thank you for your bravery in saying that. I hope it's not me. I hope it's the linked lists. Okay, let's compile it. Let's run it. And let's see what it did. I mean, it did nothing because I forgot to print out the list after any modification might have happened. So that's incredibly unhelpful. Let's try that again. Okay, let's compile and run. And what did it do? 18.11.7.5, size of the list is 4. 18.11.7.5, it did nothing. And why did it do nothing? What do we think? Why did it do nothing? Let's have a look why it did nothing. Okay, so if we want to insert at position 4, okay, quick squiz, why it did nothing? Okay, so we're over here, count is equal to 1, location is now equal to 4, and this is what I mean with linked lists. Sometimes it's such a mystery until you draw it and just sit down like this and write it out. And then you're like, oh, that's why it didn't work. That makes sense. Because you're kind of giving it a little bit of, I don't know, you're removing some of the abstract from it. Okay, so let's remove this for a second. And we'll pretend like that node doesn't exist yet. And we're still over here doing amazing things. This is still C. And this is D. Okay, so we're going to go through this thing. And it's going to basically, this is back to 1. Okay, count is equal to 1. Head's not equal to null. Current is equal to head. Perfect, I'm over here. Current is equal to head. So that hasn't happened yet. Count is 1. Check, is current next equal to null? No, yeah, good. So I'm going to go inside here. Is counter equal to location? 1 is not equal to 4. So I'm going to keep it going. I'm going to skip all of that if statement. Unfortunate, I can't see the code after it. Let's do that. Okay, great. Okay, I'm going to skip that. I'm going to increase the counter by 1, and I'm going to move my current onto the next node. I'm going to start again. Is current next equal to null? No, it's not. Go in there. Is counter equal to location? 2 is not equal to 4. So I'm going to increase the counter by 1 because I skipped this whole if statement. And I'm going to move the current across. Okay, great. Shh. Swear it's over soon. Okay, great. Check again. Is current next equal to null? No, it's not. Great. I'm going to go inside here. Counter 3 equals to 4. No, it's not. Things are going great. Increase the counter by 1. Move the current along. Okay, so now is where the magic should be happening. So let's see what happens. I go here. I check my condition. Is current next not equal to null? Oh, it is equal to null. So I don't actually go inside that while loop. So I don't do anything for it. Okay? And that's why that has been skipped in this case. So how do you think I can counter it? There is many ways to do things in coding, right? Some ways more efficient, some things less efficient. We don't care about efficiency yet in 1511, so the world's your oyster. Yeah.
You can just put current not equal to.
So I can test. One way I can do it is I can also test after I exit this, so if the counter wasn't, well, no, I can't do that.
Can do current not equal to null.
Okay, so I can do current is not equal to null. Will that work for us? Will that insert correctly? Let's check. Might do it for one case, but not, well, it compiles, always a positive thing. That's not what I wanted to do. Okay, and run it. Okay, so it's inserted it, which is really nice. What happens now if I want to, let's just double check that it's doing it at all times. So I'm going to go back and be annoying, and I'm going to check what happens if I insert in the middle. Okay, let's see if it does it now. So recompile, run it again. No, it's done it. It's done it in the middle. What else should I check? At the start. That sounds really great. What happens if I go at the first position? Obviously, if I put at the 0th position, that's never going to happen. So that's something else to think about when you write your code. Okay, at the start, yeah, it did it because it's doing it after. I mean, an empty list would be a nice thing to check. So what happens if I insert it before I even started creating this list? So what happens if I insert okay, will it do it now when it's an empty list? Oh, the anticipation. No, it will not, okay? And why will it not? For many cases, okay? So you're inserting 13.1, you're giving it the head of the list, which is null. And when you go down to insert at location, that's inserted tail, what you get is if head is equal to null, return head. So I'm just returning null, I'm not inserting anything. So then you would need to modify this statement in here to just insert that node as the only node. Okay? So diagrams and kind of, yeah, and just may the force be with you, linked lists. Friday you'll learn how to delete nodes. Good luck. That's the painful part. Yeah. Thank you, everyone.